Hi, CS 3140 students. Professor McBurney here. So I want to make a video to explain the Hamilton apportionment algorithm, and that's what we're going to do here. So I'm starting in this case with only 10 states. Just I want everything to fit on one screen. But let's imagine that we were trying to apportion representatives for 10 states, and let's assume that we wanted to apportion, since we're only doing a fraction. Let's say we only want to do about 100 states, or I'm sorry, 100 representatives for 10 states. So what I'm going to do first is get the total population, and this is each state and their population. So here I have Massachusetts with over 6 million, just over 6 million, Florida with almost 13 million. This is actually from the 1990 census data, but I can get the sum of the population, and I'm using Excel just because it makes everything nice and visual. You will obviously be doing this in Java code. But if I get the population, you'll see the population of the 10 states is just over 77 million. So if I have 100 representatives that I want to allocate based on population, and I have 77 million citizens, or 77 million in my population, what I'm going to do is I'm going to find the divisor. And the divisor is the average number of or average size of the population per representative, or it is going to be the population divided by the number of representatives allocated. And it turns out that just based on the numbers I picked, I ended up with about 70 or 771,000, which is fairly close to what the actual federal level is, the federal representation level is in the United States right now. Anyway, now that I have this divisor, so I expect roughly one representative for every 771,000 people, I'm going to, for each state, take the population and divide it by this number. So, Delaware divided by that number, and oops, I actually need to make a change to this formula. I need to uh, make this D2, these dollar signs here just mean this is an absolute reference. It means it's always that cell, no matter where in the table we are. So copy this formula down. Here we go. And all right, so you'll see here that Massachusetts, we would expect 7.79 or 7.8. Florida, probably about 16.8. Pennsylvania, about 15.4. And that's how many representatives we expect. The problem, of course, is that a representative can only represent one state. You can't have, it can't be like, oh, Pennsylvania and New York and Connecticut. Like if you add up their remainders, they're roughly one, so they'll split a representative. No, you can't do that. Every representative has to belong to explicitly one state. So you might be thinking, okay, why don't we just round this number? And we could try that. The problem with rounding this number is that, oops, forgot you have to include a number of digits, in this case 0. The problem with rounding this number is if I take the sum of this, so I'm going to call this my, this is how many reps allocated. If I take the sum of this, you'll see that it ends up actually not being 100. Hang on. It ends up being 99. And this is something that can happen when you do rounding, when you're trying to do apportionment. And in fact, happens very frequently. It's that you will not end up with the same number that is your total number. So, in this case, what we're going to do, instead of rounding every state to the nearest number, we're going to round every state down. Yes, even poor Delaware, who didn't really get a representative in this way, we're going to round them down. Now, 0, yeah, it's not great, but we'll fix that in a second, because then we're going to find the remainder, which is just going to be this divided amount minus the rounded down. So whatever the remainder is, this number is going to be between 0 and 1. We're going to sort that number from largest to smallest. And you'll see, hey, here we go, largest to smallest. Okay, so Delaware has the largest fraction. They're the closest to being rounded up. So we're going to give them 1. And in fact, you can see that since we have 96 reps allocated, that's the sum of this, we're going to then find that we have 4 left to allocate. And that's going to be equal to the total number of reps minus our allocated reps of 4. And I'm just going to give the top 4 states this bonus representative. And now their total is just going to be however many they got plus if they got a bonus, whatever that is. And so you can see that, the states closest to rounding up, including Pennsylvania, who was less than 0.5, they get a bonus rep effectively. So they get 16. And so every state ends up with at least 1 in this case. It is possible in a Hamilton apportionment for a state to have none, but in this case we avoid that. But if Delaware's population were much smaller, say if this population were like 300,000, then you can see that Delaware's not, or 30,000 in this case. Let me make that 300,000. Then in this case, Delaware would actually not get one because the last one would be stolen by New York. Because they're, if you sort by largest to smallest, you can see like, hey, Delaware doesn't get one. So it is possible if a state's small enough with a Hamilton apportionment, they wouldn't get any. But that's actually not the reason the United States doesn't use Hamilton apportionment. It is, in fact, the reason. There is a reason that the United States doesn't use Hamilton apportionment anymore, because the United States did use it from about 1840 to about 1880. But we will talk about that in a later video. In the meantime, though, this illustration hopefully gives you enough to get started thinking about how to implement this functionality. With that, thank you all for watching, and take care.